Okay, thanks, Chairman. Good afternoon, everyone. I'm Shijin FENG from Tongji University. My presentation is about mechanism of contaminant back-diffusion and fracture enhancing chemical oxidation in low permeability contaminated sites. My presentation includes 5 parts. First, I will introduce the background. Massive urban factories have been demolished in the past decades in China, leaving lots of contaminated sites. According to the statistics, the total area of contaminated sites in China exceeds 10 million hectares. In some sites, the contaminant concentration exceeds the standard by 30,000 times. The wide distribution and high content threaten the human health seriously. The migration of contaminants leads to the pollution of surface rivers, agriculture, soil, living environment, and drinking water. Here is a typical accident occurring in Changzhou City in eastern China. A new school was built near a contaminated site. The pH leads to serious sickness of about 500 students. Thus, the environment pollution control catches great attention in China. In the past 2 years, the investment in environmental pollution control has exceeded $150 billion. A series of national laws, regulations, and technical standards for environmental pollution prevention and control have also been published. The treatment of contaminated sites has achieved phased results in China, but 70% of the in-situ remediation sites have rebounded in pollutant concentration up to hundreds of times. The reason is that it's difficult to transport substances in low permeability formations. The residual pollutants can easily back-diffuse into the groundwater, forming a secondary pollution source. So, repair of the low permeability contaminated sites is the key difficulty. In the following part, LCS is short for low permeability contaminated sites. Physical extraction and chemical oxidation are the main repair techniques for contaminated sites. Physical extraction is the use of negative pressure to remove pollutants in the soil. The left figure is the extraction repair of a factory in Shanghai. The extraction efficiency of the high permeability soil is 50 times larger than that in the low permeability soil. Chemical oxidation is the injection of oxidants to remove pollutants in the soil. The right table shows 2 typical projects. The amount of oxidants used in the low permeability site is 5 times than in the high permeability site, but the removal rate is less than 70%. We can see that the repair of contaminated sites is not easy, especially in LCS. The mass transfer capacity is in low permeability soil is rather weak. So it is easy to repair the high permeability soil, but quite difficult to repair the low permeability soil. In our recent work, we tried to answer 3 important questions in soil remediation. Here we focus on chemical oxidation. The first one is why it's so difficult to repair low permeability soil. Physical and chemical non-equilibriums naturally occur in soil. They can largely influence the repairing process. Physical non-equilibrium is due to the local scale heterogeneity of soils. Here we call it PNE for short. Chemical non-equilibrium is due to the non-equilibrium sorption. We call it CNE for short. In order to consider the 2 types of non-equilibriums, we assume that soils consist of mobile and immobile regions, as shown in the left figure. And we assume that the sorption conforms to fast or slow sorption behavior. Then we develop a multi-process non-equilibrium in situ chemical oxidation model. We define it as the MPN ISEG model. This is a conceptual model. Look at the left figure. In the mobile and immobile regions, we consider the equilibrium mass transfer, PNE mass transfer, and CNE mass transfer. The right side shows the governing equations. Dispersion and advection are considered in the mobile region. The second order Keynote reactions are adopted to describe the oxidation process. The finite volume method is used to discretize equations. The solution procedure is built based on open form. We use sequential coupled iteration, automatic time stamping, and relative convergence criteria. We then use the results of existing analytic solutions and test to verify this model. We can see that the results agree very well. Therefore, the correctness of the numerical model is verified. We then investigate the influence of PNE and CNE in the below figure. The left part is the result of existing equilibrium model, and the right part is the result of our model. We can see that the repair process of ISEG model is much faster. This proves that multi-process non-equilibrium affects the remediation, duration, and the peak concentration of contaminants. We further draw the detailed information in the left figure. We can see that the cumulative mass and the peak concentration of contaminants in mobile region increases due to the PNE after the remediation. In the right figure, CNE causes significant trailing the remediation duration. This explains why it's so difficult to completely repair the contaminated sites. Next, we studied why we need to consider PNE. As shown in the left figure, the mass transfer coefficient alpha has a large influence on the contaminant concentration. The PNE dominant number, which is associated with alpha, is proposed as an indicator of whether PNE need to be considered. The expression of PNE dominant number is shown in the right figure. One PNE dominant number is larger than 1 advection dominates the transport and the effect of PNE can be ignored. Similar, the CNE diameter number, which is associated with second-order reaction rate, is proposed as an indicator of whether CNE need to be considered. When CNE diameter number is larger than the critical value, for example, 10 in the left figure, the effect of CNE can be ignored. We further find that the critical value is related to the logarithm of the fraction of non-absorption. Thus, we propose a prediction formula for the critical value of CNE diameter number, as shown in the right-hand figure. We have known that PNE and CNE can cause plume, chilling, and pollution rebound. Then how to assess the secondary pollution risk for back diffusion? As introduced before, when the high permeability aquifer is remediated, the adjacent low permeability soil will act as a secondary source to release contaminants into the aquifer. This process is usually called back diffusion. We consider the aquifer undergoing contamination and remediation processes, and assume that contaminants transported in low permeability formations is dominated by diffusion. Based on this assumption, we establish a back diffusion model for organic contaminants through the low permeability soils. This model considers the coupled forward and backward diffusion adsorption degradation migration mechanism of organic contaminants in a layered system. This model satisfies the boundary conditions as well as the interlayer continuity conditions. The top boundary should satisfy the source depletion model. We introduce Duham's theory coupled with the separation of variables and the transfer matrix method to solve the back diffusion governing equations and obtain the analytic solution of contaminant concentration and mass flux. We compare the concentration profiles calculated by the present analytic model with the laboratory test data. The results match well and the analytic solution is verified. Here we first show the back diffusion and contaminants from layered low permeability soils. The left figures show that the back diffusion may cause a persistent contamination plume in the overlying aquifer. Next, we compare layered and homogeneous low permeability soil cases and find that the soil heterogeneity significantly increases the plume trailing time by nearly 100 years. Then we studied the effect of source depletion model, including instantaneous source depletion, linear source depletion, and exponential source depletion. In all the three cases, we can see three stages of contaminant transport and mass exchange in the soil system. Contaminant degradation is an important process. The final experiment shows the degradation normally occurs in local zones close to the aquifer. Our results show that as the degradation rate increases, the onset of back diffusion is prolonged and the aquifer plume trailing time decreases. In addition, the results of numerous example simulation and data fitting shows that back diffusion onset time is exponential related to degradation rate. And the plume trailing time is a logistic function of the degradation rate. In addition, the results in the left figure shows that contaminant diffusivity is also an important factor affecting the back diffusion behavior. Based on extensive simulations, we can give quantitative prediction formula for the plume trailing time. Combined with the site remediation period, we can assess the risk of back diffusion in the low permeability site. While the plume trailing time predicted by the present model is significantly higher than the remediation period, the site manager should take effective measures to solve the problem. In order to solve the secondary pollution problem, the key point is how to enhance the in situ chemical oxidation in LCS. Due to the extremely low mass transfer, oxidant injection is difficult in LCS. Hydraulic fracturing is an effective method to enhance oxidant transport. Here we also developed a model for remediation technology optimization. In this model, LCS contains hydraulic fractures, and oxidant is injected through multiple wells. We assume that injection well penetrates fractures, and the mass transfer in LCS is dominated by diffusion. This figure shows a much well injection process for the oxidation repair for fractured LCS. The oxidant enters the hydraulic fractures, forms the injection well, and then enters the surrounding low permeability soil by diffusion. In this process, the fracture reduces the transport distance of the oxidant and hence shortens the transport time and achieving enhanced delivery. The governing equations are solved based on the Laplace transform in the time domain and the Fourier cosine transform in the space domain. Periodic injection and slow release oxidants can be considered. Comparing the agent concentration distribution calculated by the present model with the numerical results, we can see the results agree well and verify the solution. The left part is oxidant injection into LCS with hydraulic fractures, and the right part is that without fractures. We can see that after hydraulic fracture, the injection efficiency is significantly improved and the repair time is shortened. In engineering practice, well spacing is important. We must have a cost-effective design. Based on this model, we find that low fluctuation in concentration improves the use of oxidant. The evaluation of the effective delivery of fracture agent is based on 2 points. One is the spatial distribution of the oxidant concentration, and the other is the effective residence time of the concentration. This model analysis reveals that injection time and wear spacing are effective controllable parameters. The right figure shows the fluctuation characteristics of concentration in fractures with different wear spacing, injection time combinations. We have known that remediation efficiency can be enhanced by hydraulic fracturing. Then, how to design this system for different soil conditions and contamination distributions? We propose a design flow chart as shown in the left figure. The fraction program, oxidant demand, wear spacing, and injection pattern can be optimized. The right figure shows the result of fraction remediation. Comparing with direct remediation, we can see that the scope of repair is improved nearly 3 times after hydraulic fracture. Therefore, enhanced remediation of LCS can be achieved by proper hydraulic fracture and oxidant injection. The final is the conclusions. Okay, finally, I want to express my sincere gratitude to my group member for this work. Thanks for your attention.